tools and practices for transparency and reproducibility in the social sciences. Today is our third of 4 online sessions. So today we have Carla Palos Castellanos from the California Policy Lab, which is here at Berkeley. She'll be presenting hashed linkages for administrative data sets. And then we have one final session on December 6th, which is how to evaluate journal implementation of open science standards, the trust process, and that will be presented by Sean Grant at the University of Oregon. So please see our event for details about the ORS session 4. So you don't miss any updates. Make sure you're subscribed to our newsletter. You can do this on our website, which is bits.org, or you can follow us on Twitter, which is UCBits. We're also excited to announce that we've published our call for speakers for the Spring 2023 ORS series. So if you have a new tool or practice for increasing transparency and reproducibility in the social sciences that you would love to showcase, we're inviting you to apply. The deadline is December 23rd, and there will be more information about that on our website and Twitter as well. So without further ado, I'd like to introduce our speaker for today. At BITS, we're very, very excited about Carla's session. This is a particularly new tool and topic for all of us. And so I think we're excited to see what she has to show us and to learn about the tools that CPL is using. And so I will turn it over to you, Carla.
You're great. Also for organizing. I'm really happy to be here with you today. Before we begin, I just want to do a couple of housekeeping items. So the first questions, I'm joined today by from CPL, so Jennifer Hogg, she's a research manager, and Sarah Hoover, who is a data analyst. They'll be answering your questions in the chat throughout the whole presentation. I will also have 2 or 3 which you can unmute your mic and ask your questions, and I will let you know when those are happening. And the second point that I wanted to make is that this is the output of a lot of work from current and former CPL staffs, and there's still a lot of work in progress. So if at the end of this presentation you decide to adopt our toolkit and our code, we're always happy to hear your feedback and thoughts about it, so please let us know. The third thing that I wanted to mention is that our code, which is already available on GitHub, our toolkits are available on our website, and finally, the slides will become available to you at the end of the presentation. Started. Okay. So I'm gonna start by providing a little bit of context. So the California Policy Lab is a nonpartisan research institute based on the University of California. Our mission is to improve the lives of Californians by generating evidence transforms public policy. We focus our work in 6 different policy areas: education, criminal justice reform, poverty and the social safety net, labor and employment, health, and homelessness and high needs populations. We work with over 40 state and local government partners and focus almost exclusively on administrative data. As you can see here, we have data on wages, business systems, enrollments, K-12 and higher ed, and a lot more. So oftentimes the impacts of some of these policy areas extend far beyond the data that the departments executing this policy might collect. And as you can imagine, our research also crosses these different policy areas. So for example, you might be interested in learning more about how the social safety net impacts health, employment, education, etc. This is the reason why we think that linkages are such a helpful and important tool in connecting siloed data in order to help answer some of these very pressing questions. And why do we do it? So I'm gonna get you started with a little bit of terminology. So first of all, what is a hash linkage? So a hash linkage is a way to join data sets that typically contain personally identifiable information, or PII, as you will hear me say throughout the presentation, that we wouldn't be able to see for a number of reasons, and we'll go over that in the next slide. It does this in a way that it preserves the privacy of the PII. And as you can tell from the name, it has two main components. So onto hashing. Hashing is a method of turning readable data into unique but unreadable data via a one-way encryption process that cannot be reversed. This is what allows us analysts conducting to distinguish between two different values, but ensuring we never see the underlying sensitive data. So in other words, two values that are equal before the hash will remain equal after the hash. Two values that are unequal will still remain unequal after the hash. And we apply this strategy to different identifiers, including first name, last name, date of birth, social security. And we do so in a way that we can still link across data sets. So again, the goal is to look at two different data sets and using the PI without actually seeing it, say that they are the same person. The other thing that we're going to talk about regarding hashing is how do we go about imperfect data. And we're going to talk about that once we get to the linkage. So linkage, this is the whole reason for this presentation. The linkage allows to identify, again, who we think is the same person across two different data sets. The way that it works is that different agencies send us hash PII and non-hash analytical data. And because this hashing has been done in a consistent way across the different data sets, CPL or a third party is able to link these data sets in a meaningful way. And again, I already mentioned this point, but I just really want to reiterate that the reason why we do hash linkages is to understand more about the populations that the different government agencies are trying to serve without compromising their privacy. So a lot of the times an agency might have only one part of a picture, and linking this data provides a much richer understanding of these groups. So I'm going to start with a very high level use case. So in here we have two different agencies. Each of them have PII that they don't want to share or they can't share for any reason, which obviously means that we cannot do a linkage. They might not be able to share the PII for different reasons. Among them, it could be technical capacity, but more likely than not, it tends to be legal restriction. There are always also privacy and security concerns. But it could also be due to trust issues. If two agencies have never worked with each other before, they don't know if their goals and if their goals are actually like shared, if they feel confident enough sharing this data with another agency. In the scenario where we do have two agencies that can share the data, they can encrypt this information and then have it linked. But even with this capacity to hash and link the data, some agencies might not be able to do so unless they have a third party helping facilitate the linkage. So in the case of the work that we do at CPL, we serve as a trusted third party intermediary to facilitate these linkages. So in order to generalize a little bit about what hash linkages are, I'm gonna provide a case study. This is what we refer to as a CREFC experiment. So if you want to read more about this, it's on our website. But the premise of this study was that in 2021, the California Department of Social Services, or CDCEC, expanded the eligibility for Supplemental Nutrition Assistance Program, SNAP, or CalFresh in California, to include students with an expected family contribution, or CREFC, of 0 in their financial aid applications in response to the COVID-19 pandemic. At this time, the California Student Aid Commission, or CSAC, ran a randomized controlled trial to test the outreach, informing students of the new eligibility rule and encourage them to apply via a simplified portal, which was administered by an organization called Code for America. So the main research question we were trying to answer here is, does outreach to college students who are newly exempt from the CalFresh student eligibility rule due to having a CREFC on their FAFSAs, induce them to apply to CalFresh and ultimately get enrolled. So as you can see here, we can think about this as a three-party linkage problem. CSAC contains all of the student information. Code for America contains application information about that specific portal. And CDSS has information regarding who actually ends up being enrolled in CalFresh. So again, the question is, of the eligible students who were notified, how many they applied and how many they end up being enrolled? So using this same framework, going back to the chart I showed previously, and here we can see, for instance, two agencies, Student Aid Commission and the Department of Social Services. Each of them has PAI. They hash this data, then they send it over to a third party, in this case, CPL, and we're able to link that data. So with this framework in mind, we can talk a little bit more about what hashing is and how they work before we talk about how to implement one. So the hashing technique applies an algorithm. At CPL, we use SHA-256 to the PII, converting strings of data. So for instance, my name, social security, etc., into unique hash values or string of characters that can no longer be identified. And it has a couple of main characteristics. The first one is that it has no collision. So what this means is that no two distinct original values should produce the same hash value. Otherwise, we run into the possibility of hash positives. So for instance, Rob and Ruth, and you don't want that. So in the example that we're seeing right here, we have a social security that is 1 through 9. Even if you change that PII slightly, so changing the 9 from the 9 to a 0, it produces a whole new hash value. And similarly, you can think about this problem as similar outputs will equal same outputs will inputs will produce the same output. So you can imagine a case in which you have a John in the data set. Every time you see John, it should have exactly the same hash value. The last point is that it is irreversible, and this is one of its most important characteristics. Since we apply this one-way encryption algorithm, there is no determinant to work back to the original value from the hash value, even if you know the function and the hash value itself. Otherwise, it really wouldn't be privacy preserving. But in order to ensure the privacy, even like providing another safeguard, we add the second component, which is what we call a salt. So a salt is a string of text that is added to the PII before it's hashed. And in practice, only the partners who are hashing the data should know what the salt is. So us as the third-party intermediary should never know what the salt is. And why do we add it? The salt prevents brute force approach to trying to reverse the hash. So although we said there's no deterministic way of trying to re-engineer a hash, you can imagine a scenario in which someone is going with a brute force approach and they're trying different hash values, and they know there's multiple Johns in the data, and they find one that works and they can try to back up names that way. So we introduce the second security layer in order to really ensure that this the privacy is preserved. So as we mentioned in the previous slide, since different original values always output different hashes, adding the salt will always output a whole new value. So if we look here in this example, we have the social security 1 through 9. We're adding the salt. I love apple pie, which is again just a string of characters. And if you see the outputs, there are completely different outputs. So some general recommendations as to how to pick a salt. We usually say, pick something strong, something that has numbers and letters, lowercase, uppercase. At the end, it doesn't really matter what it is. You just need it to be consistent across all the partners. So everybody who's gonna be hashing for the same project, you want it to use the same salt. Otherwise, you will not be able to meaningfully link this data back together. So before I jump into how to put a hash into operation, Are there any questions? Okay. So now we're gonna talk about the steps to hash. Okay. So the first one is to get the legal agreement, so the data user agreements and IRBs in place. Obviously, there is a lot of work that goes into setting these agreements in place, and a lot of people actually. This is not what I will be talking about today, but it's again already on the chat, so feel free to think on that. The second part is data request. So once we have the legal and technical permissions in place, this mainly consists of requesting the data and working with the partners hashing the data to understand the process. The now that like 1 and 2 are complete, this is where the so what we do is interview the partner staff, environment, and the data. And we'll talk about what this interview is in the next couple of slides. The next one is to modify the code if where the partner to hash the data. And this is on 3 components. The first one is the salt, syntactic test data, and then finally hashing. And then finally, there's going to be a troubleshooting that happens. It doesn't just happen at the beginning or the end. There's going to be a lot that happens throughout the project. But I think one of the main things that I want to highlight is, aside from the technical piece of the hashing, is that this really is a coordination exercise. It requires a lot of work from the program managers, the research managers. So folks to build as much time as you can into your timeline, and just be transparent about the process. Hiccups happen, and most likely they're not. So something like the hashing can take a really long time, more than 1 to 2 weeks, because you're troubleshooting and going back and forth with someone. The data extraction, instead of taking 2 months because of restrictions of time availability with your partner, may end up taking 6 months. So just have these things in mind. But in a good case scenario, you can imagine that this can take anywhere between 9 to 12 months from start to finish. But again, it's really dependent on all of these different components. So you might not want to follow all of these steps, but these are some of our best practices. So when you're working with a partner, we recommend that you identify the correct data and hashing points of contact with the project manager. And just a note, this might not be the same individual. The second point is that to put together an explicit data request. And I cannot emphasize enough how important it is to set a good data request. You need to be as specific as you can about what you need. The scenario that you're trying to avoid is have an agency pull data for you, hash the data, and then it turns out that that's not the data that you actually needed. So really thinking about this in advance can help save a lot of time down the line. So something that you can do is clearly define the universe upfront. So for example, the universe you might want for your project is all of the CalFresh applications that were started but not necessarily completed or submitted between January 2020 and December 2020 through the org portal. So again, be very specific about what you need. Identify the variables that you want, the years of data that you need, and identify what variables you need to have hashed. So at CPL, we usually do first name, last name, date of birth, and social security. But for your specific project, you might also want to include addresses or phone numbers. So be very clear when you're setting that request about what data needs to be hashed and what data doesn't need to be hashed. The next one is gathering requirements. So again, you can set up a technical interview with the partners to discuss some of these things. So some of the things that you might want to get to know is what programming language they want to use. So right now we have available hashing code in Sass and in Python. So you need to know what language the partner is going to be using. know also what operating system they're using, if they have memory and disk space constraints. Other things that you will probably want to know is what are the primary keys. So this will come really handy trying to link the data. You also want to know if the PII is all in the same file. So first name, last name, date of birth, and social security are in the same file, or if these components are spread through different files, because this will inform how you have to edit the hashing code. Other things that you want to know is the format of the data. So what is the delimiter that they're using? Most of the time is comma, but that doesn't necessarily mean that that's the case for your partner. If there are specific formats of the date variables, if there is a special encoding that you're using. So as I'll show in a moment, we standardize the data as much as we can before hashing it, but knowing if there is anything that they do with special characters in advance will be really useful to know. Other things is things like quoting. So Python, I believe, does double quoting by default. And this is important because there are times where the input file that you're feeding into the hashing code doesn't match the length of the output file, and quoting could be an issue. That could be part of the reason why that happens. So knowing this in advance will save some time troubleshooting. Other things that are important to know is if folder for missing values. So for instance, if they have a missing social security, do they just leave it blank, or they just put like 1 through 9, right? Like these are some of the things that you will want to know. Again, this list is not exhaustive, but really interrogating the coding environment of the partner will help you save. This is especially since we cannot see the data. So it's almost like drawing blind. So it's really useful to know this in advance. And then finally, define the role and set expectations. So again, you want to meet with a partner to talk to them about how the salt works. This is something that, again, you're not going to be, you cannot know what the salt is. You can help them facilitate the salt meeting, but you cannot be in the room when that happens. So letting them know that that is a step that they're going to have to take is really important. Other things that you should do is walk them code is and what they're actually going to have to do with them, how they're going to send the data back. So obviously you don't want people's data floating around the internet, so don't send it over their email. So you will probably want to transfer protocol, but again, it really depends on the project you're working on and the partners we're working with. This is it for this section. Taking a step back, not that we covered some of the conversations that need to happen. You're at the point in which the partner already knows the salt. They already have your hashing code. They already pulled the data and they're ready to hash. Before they do that, they really need to test their hashing code and the salt using a synthetic data set. So we asked all of the partners working in the same project to use the same synthetic data set. They're also using the same salt. And we asked them to test it on a dummy data set. And I'll show you an example of what that could look like in a second. And the reason why we do this is that you really want to check if the salt is being used consistently across your partners. So if one partner forgot to add a character in the salt, you will get a different output. So you want to make sure that they are using the same salt. If the coding environment of one of your partners is doing something funky, raw data looks like, it is easy to check if the partner's code is doing what it's supposed to. So again, you don't want the partner hashing a million records and then realizing that the hashing was done incorrectly. So this is what we asked them to do, the synthetic data set. So here's an example. You don't have to use this example, but some of the things that we recommend doing when testing the data is to keep it short. You're not actually testing the full code with them. You should have already done that in-house. So we ask you, like don't put more than like 10 rows. Again, if all of the partners code is running the same and all of them are using the same salt, these 10 rows should be exactly the same across all the partners. We also recommend to test edge cases. So for instance, in the first row, here I have an E with an accent. So if the hashing code did the thing correctly, which includes cleaning, it would have removed that accent and converted the E with an accent to an E without an accent. The last thing that we recommend is to include examples of all of the variables that you're hashing. So again, most of the time we're only doing first name, last name, social security, and date of birth. But if you're also doing phone numbers, you definitely want to include some cases for that. So I cannot emphasize enough how important this step is in the process. The challenge that we're facing here is that there might be data cleaning happening on your partner's computer. They might be doing things that we cannot actually see because, again, we cannot see on hash PII data. Since we don't have this visibility, we cannot really know how well we did with our hashing and subsequently with our linkage. So this is why putting this quality assurance checks in advance really helps at least provide some sort of standardization. And with that being said, once they do this check with the test synthetic data, you can, and it matches across all of the partners, you're ready to go. You can tell your partners, you can move on to the hashing phase. So now we're going to talk a little bit about the code. In general, what the code does is that it normalizes the data. So it converts everything to lowercase, it removes white spaces, removes punctuations, standardizes the spatial characters. We also chop up the data. And this is gonna sound kind of funny right now, but once I get to the linkage part, it's gonna become clear why we do this. So what we mean by chopping up the data is that, for instance, for the first name field, you might wanna get the first 2 letters, the first 4 letters, and I don't know, something else. You might want to do the same split of the social security, maybe getting only the first 7, then the next 7, and so forth. And then the next thing that it does, it adds a salt to the main fields, as well as this like substrings or these chopped components. And finally, it hashes the data. We apply the SHA-256 algorithm to each piece of the salted data. And right now, I'm just going to give a very quick run through of what that code looks like. Again, we have this in Python and Sass. I'm only going to go over what it looks like in Python. So our Python code consists of 2 main components. The first one is the actual Python script, and the other one is a configuration file. Your partner shouldn't really have to modify anything on the actual Python script. They should just be working with this configuration file. And the things that they need to edit are things like the salt. They need to put whichever salt they agree upon themselves, the names of the columns. So it might not be SSN for them, it might have some other name. Input file path, output file path, the delimiter that they're using, the last year of acceptable date of birth, either a specific date format, and very we have this parameter right here, which is dropping on hash PII. Again, where the scenario that you're trying to avoid is for them to send you on hash PII. So this parameter should always be set to yes, unless you're doing debugging. With that being said, what the code does, it will go to the social security section, for instance. It removes all non-digit characters. It pads the social securities to 9 characters. And then finally, we create this tags right here. In here, this one is called bad SSN. We do the same thing for first name, last name, and date of birth. And this might not be immediately important what we're doing it, but we use it during the linkage process. If, for instance, the social security is a key component of your linkage, you probably want to make sure that the quality of that social security is good. So in here, we identified a bad social security as something that has as something that it's missing. If it has more than 9 characters, if the first 3, middle, or last numbers are all zeros. If it starts with 666, if it starts with 9, if it's 9 consecutive numbers. And there's this other one which you can read more about why that one is there. Later, it was actually someone's real social security that got exposed back in the 40s, and so now we just include it as an invalid social security. From here, we create the substrings that I thought I'd talk about of the chopped social security, and we create 8 versions of that. We remove titles, we remove prefixes, we make everything lowercase, strip, standardize special characters. And finally, we create this bad first name flag. For us, a bad flag is just something that it's missing. And from here, we create again these 4 components. So for us, we do the first 2 letters, first letters, and the soundix. The soundix is just a phonetic transcription of the PAI. First name for date of birth. We don't really do any real cleaning. All we do is just break the date of birth into 3 different components: year, month, and day. Our backdate flag looks like something that it's missing if the date came before 1900, or if it comes after the latest year that we had determined. From here, we just append the salt and then do the hashing. And this is really all we do with the hashing code. Okay, so with that being said, I know we just went over a lot of material. Are there any questions? Are there any questions in the chat? So awesome. Okay, so now we're going to be talking about linkages. We're of course going to be talking about linkages in the context of a privacy preserving or a hash linkage. There are a match, but the way that we do it in GPL is using a set of rules. Paper on our website, so you're welcome as well. A lot of time. And so the scenario that we're seeing right here is that we have 2 different agencies. They each have data representing probably the same real-life persons, but we don't have a common identifier. If we did have a common identifier, probably wouldn't need to do a linkage in the first place. A constraint that we cannot see that person's real life information. So we cannot see their first name, last name, etc. So the question becomes, how can we in multiple data sets where we are restricted from seeing the identifying information about that person? The way that we do this is by irreversibly obfuscating the data in a way that preserves equality of the regional values. I hope this sounds familiar. This is what we've been talking about so far. It's the hashing. And again, because of the qualities of the hash, to equal original values will always yield the same outcome, the same hash. So in the example that you're seeing right here, if you look at John, so John has the same hash value every. So how do we go about like merging or linking this data? We can go which is to just go based on exact equality of the PAI. And the procedure will go something like this. You have partner A sending you hash PII data plus some unhashed identifier. Partner B does exactly the same thing. You go and you perform a merge using exact equality, and from there you get a crosswalk, and you're done. So, example, here we have the data. These are the two matches. We drop the non-matches. From here, we only retain the identifiers at this point because you already identify who is the same individual, that PII anymore. Once you have this crosswalk, you can either send it back to your partners and have them do some work. And in here, what you can see is that the partners never really saw each other's PII hashed or unhashed. They only get the output, which is the crosswalk. Or the other thing that you can do is, just conduct some research in collaboration with your partners. But I think a more interesting scenario, and more likely than not, the scenario that is not perfect. Here, I have my name in two different agencies. One of them is spelled with the C, the other one is spelled with the K. And this is actually a very common issue. You can also have issues in the Social Security, like two numbers being two adjacent numbers having the reverse order. So instead of being 8-9, you might have 9-8. So when we look at this example, we can clearly tell that this is the same individual. They have the same first name, same last name, same Social Security. But if we went with a naive approach, we will not actually get a match here because that one starts with a K and the other one starts with a C. So how do we go about solving this issue? We use so the general principle of some measure of string similarity such that two different strings or PII can be declared sufficiently close to equality. And what we mean by sufficiently close, we're going to be discussing in the next couple of slides. So the question becomes, if we can only check for exact equality of these alphanumeric strings that are protecting our data, by the way, how can we do fuzzy matching? And the answer here is to create substrings of that original PII, hash it, and then run the comparison for exact equality. So you remember back to the hashing code I just showed you a second ago, the hashing code was creating these subfields. So for the first name, it created like the first two letters, first four letters. For the Social Security, it created a couple of substrings. So again, the solution is to create substrings or features of that PII. So in the example we were looking before at John, and here we have two agencies. One has John, the other one has Jonathan. What we did by creating this feature is creating the first letter and then first four letters. So just taking a pause at CP Social Security's fuzzy fields, 8 fuzzy fields. So we create 8 versions of the Social Security, each of them with 2 digits removed. And again, what we're trying to capture with this is adjacent mismatch digits. So 8-9 versus 9-8. And with the first name, we do the first 2 letters, first 4 letters, and soundix. Then for last name is the same. And with date of birth, there's no real fuzzy fields, but again, we can break them up individually. So going back to our example, we're seeing John and the full first name is not actually matching, but the first letter and first 4 letters and the last name do match. So depending on what you consider a match for your specific linkage, we can make a case that this is actually one. So again, our question is, how close is close enough? At CPL, we have used first name. We have used the first 2 letters, first 4 letters, and the soundix. And we usually see that this tends to be a pretty good, it does a pretty good job at capturing this preciseness. But if for your specific project, you don't want to take that and you decide that you only want to keep matches that are the exact same thing, you're welcome. A lot based on your intuition and the project that you're working with. And there are trade-offs that you will have to make based on depending on what you end up picking, and we'll go over those in a second. One thing that we want to flag is that, be aware of false positives. So in here, for instance, we have Samantha and Samara, which obviously the first names are completely different, but their subcomponents actually match. The challenge that we have with these false positives is that they're very hard to determine beforehand, and they're very hard to capture after they're done. So this is why thinking about your linkage strategy in advance is really, really important. So going back to our question of how close is close enough, we are going to answer this question using two definitions. The first one is rounds, and the second one is scores. So a matching round provides a level of stringency to categorize how good the match is looking. So for example, we have round 0, which is our strictest match. It has to have perfect match on social, first name, last name, and date of birth. And you might want to create different matches that need different levels of confidence for different applications, especially the ones with that can lead to like false positives. So a scenario that I can think about is, for instance, you have a match, you want to do this linkage for the purpose of creating a list of people that you want to do some outreach to let them know that they qualify for some program. And if you a lot of like fuzziness here, you might run into the risk of letting someone know of something of disclosing someone's personally identifiable information by accident. Whereas, for instance, if you're just doing some like summary statistics, having a looser restriction might be okay. And as I have been trying to explain so far, this rounds or these combinations of criteria are, a lot of it's I think more than a science, is really an art. A lot of it comes from your knowledge of the data, your intuition, and like what you're actually trying to produce here. So the second component are the scores. So scoring is a way to quantify the quality of a match of a given PAI field. So, for instance, a match on the first name, full first name, so my whole name with a whole string, Carla, is the strongest thing. It will receive something like a score of 100. Don't worry so much about the actual numerical value. Just think more about the order in which it comes in. And again, just like with matches, these are typically done via like introspection and knowledge of the data. What these things, how you decide these things are hard to know like ahead of time. So whether the first 4 letters and the first name are more indicative of a true match than the first letter and the phonetic transcription, it's really hard to know in advance. So one thing that we do recommend is start by listing the hierarchy of the strength of the possible matches fields. And again, a lot of this is just informed by your intuition and knowledge of the data. Yeah. So in summary, I think what I want to like state here when we're thinking about how close is close enough, even when you're using these rounds and this scoring, these are not fixed. These are things that you have to decide for your specific project. You can add or remove or change as many of them as you want. This is going to vary by project. This is going to vary by agency. And I think the hard part again is that it's hard to know whether you're doing like what is good or bad because you cannot actually see the data. And on the same note, it's difficult to tell whether you did a good job or not. What the true matches were, we would just, of course, use those. But 2 approaches that we take to try data. validate on non-PII fields that exist on both agencies. So an example of this could be income. Another thing that you can do is get a measure of the quality by the rate of IDs that match to other IDs on the other data set. So if you're seeing multiple instances of, to, I don't know, 50 IDs on the other data set, it's probably a signal that something is up. So we won't have time to cover this in depth, but I will provide just some general overview of how you can determine your linkage strategy. So to develop a linkage strategy, you need to really survey the PII fields that you have on your data and think about what partial fields you want to create. So what I mean by serving the PII fields is that if the Social Security is going to be central to your linkage, and one of the data sets that you're linking on has something like 30% missing social, you might want to really think about how you're going to approach that fields. Again, you need to determine what you're going to need to conduct this linkage before you even do the hashing. So if, like I said, like we provided you a list of what we typically do at CPL, and it depends on your specific project. You also have to think about the definitions of bad data. When we were going over the hashing code, I showed you what we consider at CPL bad data. You might think that, that's too strict. I want to do like something a little bit more looser, and you're welcome to do that as well. And again, we briefly touch on matching scores and rounds, but I encourage you to look at the rest of the slides. They provide a lot more detail regarding what the matching scores are, the matching rounds, and how to use them. But I think before I conclude, one of the things that I want to really emphasize on this linkage strategy is that we have been talking so far as hashing and linkages as being two separate processes, and even some that happen in a sequential order. But I really want to challenge that and have you think that, the linkage strategy has to be decided before you even start hashing, right? Because whatever you decide that are the important fields to break down, whatever fields you decide to use, all of that has to happen before you even jump into doing the hashing. So a lot of what you're going to see or experience when doing a hash linkage is a lot of like iteration. There's a lot of going back and forth. And this is common. And this is very common when doing something like this. So with that being said, like I said, you're welcome to look through all of these slides on your own time. So before I jump into some of the takeaways and provide some resources, I want to ask if there are any questions. I know that what I just presented was a lot of information, so I just want to take a pause right now. Okay, so the main takeaways are that hash linkages help break down data silos, which can help break down policy silos. Hash linkages can preserve privacy, which again help break down those silos. So if a partner trusts that you're gonna keep their information private and secure, they're more likely to work with you in order to execute this hash linkages. And finally, the linked data can help identify problems and evaluate solutions, which creates this cycle of feedback. So this is what we're seeing in the data. We can probably think about another linkage or how to use data that already has been linked to continue providing solution. And with that being said, here is a list of the resources. So the first one is the toolkit that we have. There's a lot more other resources in our website, but that one takes you to the main toolkit we published. Our code, as I mentioned earlier, is available on GitHub. So you're welcome to look at it, work with it, and send us feedback. And then finally, the slides, you can find them using the last URL code. Okay. So without stop sharing.
Thank you so much, Carla. We have a bit of time, so I wanted to highlight one question that I see in the chat. Someone asked, does each project require a new round of hashing?
That is a great question. I think that it much. It depends. So for a similar project that would use similar data, then you probably wouldn't require a new set of hashing. They already know how to work with each other. They already know that we're going to be using the same data. But if, for instance, you are trying to link data between those, like you want to use data between that has already been hashed, but there's a third party who doesn't want to cooperate with the other two, then you're probably going to have to produce a new hash. So it really depends. And I think that goes back to an earlier point of how long things take. This is part of the reason why it might take some time. So if you're using the same data for similar projects or with similar goals, you probably won't have to redo the hash every single time.
Thank you. Another question is, for scoring match quality, is there any empirical basis for how to map different rounds of matching to numerical scores? So for example, something you could use to derive regression weights based on potential for measurement error. That's in the chat as well, if it's helpful for you to reread it.
Yeah, I think that this is a great question. I probably will have to sit down and think a little bit more in depth about it, but feel free to reach out to me via email and we can think about this. Any other thoughts, questions? Anyone who's ready to jump into doing hash linkages? So if there are no other questions, I want to take this opportunity again to thank the whole BIDS team for organizing this wonderful event and for having me here today, and also my my colleagues for jumping in and answering questions.
Sorry, Carla, we do have one more. Maybe we can just take this as the last one.
Yes.
Yeah, I'll let you.
Can you, for Michael, I hope I'm saying your name right, can you provide a little bit more?
Yeah, sure. I guess first of all, this is great. Like we've done some work like this at RAND with some partner state agencies, but I don't think at least the projects I'm on, we haven't moved to this approach quite yet. But the question I was getting at is sometimes there's data that government agencies or public sector entities have that comes in from private sector partners. My experience with this has mostly been with state all-payer claims databases, which California is building one right now that's I think about to go into production. And we've worked with a state that used, as far as we can tell, a much less sophisticated approach to hashing that I wish they could see your presentation and avoid some of the errors. Like they really just hash everything together, and if there's one character wrong, they fail to match, which leads to all enormous problems you can probably think of. But they've had situations where like they've had to tell the data users like a year or two later, oh, we realized that like this health insurer implemented the hash wrong and there isn't really a way to fix it. So they it ends up creating huge problems. And I'm just thinking about like an all-payer database that exists in California that we have worked with, which is the workers' comp data. There's very widely varying levels of sophistication among private sector players. And, like on the workers' comp side, the claims administrator might be like a huge insurance company. And maybe they have a lot of data scientists and stuff. And then another one might be like a small county government or like a small joint powers authority. And I'm just curious if you've gotten into bringing in sort of like data sets that originate in the private sector and whether you've run into implementation problems with hashing. I mean, the same question might apply to maybe like departments of varying sizes or agencies with varying levels of technical staff within state government as well.
Yeah, I'm here. I'm also going to pull it from the expertise of my colleague Jennifer. My understanding is that we're currently not working with the private sector.
Got it.
Other
Thank
point
you.
that you brought up with working with different agencies of various sizes, we do see that. And as you mentioned, different teams have different, I suppose, resources and how they can like clean and manage the data before it is even hashed. So you will see, we have encountered like discrepancies, and as you mentioned, a really big challenge is if you know that they hashed this data and they hashed it incorrectly because of this discrepancy, then it will be really hard to reconcile those differences once you're doing the linkage. So again, as I mentioned, a lot of this is like kind of driving like without being able to see. So what we try to do is just try to implement as many checks as we can along the process. So that's why I emphasize so much like the synthetic data set, because you're not going to be able to cover everything, but at least you can guarantee some kind of standardization from the beginning. And I'm not sure if that answered your question, but I think that's the closest that I think we have worked with.
Great. Thank you. Yeah, but really great presentation. I learned a ton.
Awesome. Thank you all for joining us today.
Wonderful. Thank you so much, Carla, and thank you to her colleagues at CPL. Just a reminder that we have one more session in this fall ORS series, and that will be on December 6th, how to evaluate journal implementation of open science standards, the trust process by Sean Grant, and we will be sending out reminders and tweets about that, and you can still register. It is open and free to everybody. So thank you again, Carla, and thank you for the great questions and participation, everybody.